Good morning, I'm Allison Basili, and today I'm going to talk about my research on using surface plasmon resonance as a nanomolar measurement tool. SPR is a somewhat recent development, and its story didn't begin until 1902, when Wood noticed an anomaly in wavelengths that are reflected from a metal diffraction grating versus the original light waves that were presented to the grating. It took 39 years before theoretical analysis assumed plasma to be the culprit of those light waves. In 1968, two scientists physically proved the occurrence of surface plasmon resonance as the culprit simultaneously. And then in 1983, the Kretchsmann configuration, which I'll be using, was first used to exploit the gas in research for research purposes. SPR can be used in biorecognition, healthcare diagnosis, food safety, and drug screening, which is my focus, and it allows real-time, highly sensitive, and highly accurate sensing of small sample sizes in what is now a cost-effective and sustainable system. Plasma is a quantum electrified gas, such as lightning, and its quanta are plasmons, similar to how photons are the quanta of light. At specific angles dependent on the adjacent medium, applied to a metal film, the Kretchsmann setup, which is what I use, allows plasma to be propagated along the surface when light is applied. Using a full spectrum of light allows the reflectance to display the clear anomaly of which wavelengths have been absorbed. By doing that, we can tell what medium has been applied to the gold film. This is my experimental setup. I've got this collimated white light source. It goes into a fiber optic cable and then shines through a prism onto a gold film, and then I can use a slip cover to introduce a liquid adjacent media if I'd like, and then reflects into this collecting lens, which is then collected to the spectrometer here. It's kind of hard to see, and the spectrometer plugs into a computer, which then plots the percent reflectance for every wavelength. So this dip will tell us what the resonance wavelength is, and then that can be used mathematically to determine what N value we've got against the gold film. So my steps are to turn on the light, set up the software, collect background noise, and then apply whatever liquid media to the film that I want to collect data on. Adjust the angle by moving the cages. They are adjustable to get the best angle possible. Then I take my picture from this parallel surface so I can get a parallel picture, which I can then analyze in the image software to collect the angle data. Then I can copy the spectral data to my clipboard and put it in an Excel sheet, which I can then use for data analysis. And then I can repeat those steps for different media as I'd like. This is what it looks like when I measure the angle. So as I said, I take a picture. This was just me testing the software here. But for example, I would place a grid over the picture in line with one of the cages, and then align one line to that grid and one line to the other cage. And I would do this several times for one picture. It would give me this angle here as a measurement. I would take the average, and that would be my final angle measurement, and then I would use the range as the uncertainty. This is what the inside of the spectrometer looks like. Here's where the fiber cable input is. There's a slit there to limit the light input, and then a wavelength bandpass filter. Then here, the light waves are parallel due to this mirror here, which just makes it less of just this crazy beam and a clear parallel light source. This is a diffraction grating, which separates each wavelength by its wavelength. And this is a focusing mirror. And then the sensor here can see how much of each wavelength is still available after the reflection. And then this number 8 here converts that measurement to a digital system that can then be plotted in the software. Here's the derivation. This is the light wave equation, and here's the Plasmon equation. So if you look at this picture here, where here is the surface plasmon propagation, it absorbs the most energy when the whole light wave is absorbed. So that's why at resonance, these two equations are equal to each other, and we get this resonance equation. It's also important to note, like I said earlier, this imaginary I, this K value is given to us, and that's just the imaginary part of N. And N is the refractive index, and it's also equal to the square root of E, which is the dielectric constant. This is my error propagation, and this is the uncertainty for N that I'll be using in my data analysis. So I was given a reputable source of corresponding wavelengths and values for gold. Then I imported that data set into a Python code. And then I was able to interpolate to get a data set of 1,000 different wavelengths that are expected at specific incidence angles and adjacent media indexes. This is supposed to say theta. So for example, if I measure 650, let's say, so along this green line, and at an angle of 78 or 79, that would be around here. So that means I could expect the N value of the adjacent media to be about 1.35. Or here would be 1.35, 1.36. Okay, this is an example of collecting one data point. So this is the plot that the spectrometer creates, and here's the dip. The lowest value would be our resonant wavelength. And I told you how I collect the angle. So X would be the angle and Y would be that resonant wavelength. Here's just a rough analysis. This was me practicing the setup and making sure it works correctly. I did it for air, water, and a lab alcohol that I had. So this was the expected N value for the adjacent medium I introduced. And here were some N value lines that I got from the data that better matched my data. And so I averaged those two to get an average experimental measurement of N, but this is obviously just a rough fit. And in this data set, I omitted these two data points because I realized that the spectrometer begins to get a bit noisy past about 750 nanometers of wavelength. So I learned to omit any wavelengths past that in the future, which was a good lesson. And like I said, since it's a experimental error, I omitted those data points. Oh, and as well, there was a systematic shift each time from the expected N value and what I was measuring. So analyzing that first data set, I did get an average shift value of about 0.04. And then the percent error wasn't too bad for a physics experiment, but it was a little high for a measurement device that we're wanting. But after incorporating that shift, just subtracting it from the measurement and then finding the percent error, it was actually pretty small. So that shift was very significant, and I started to wonder what caused that measurement shift and will it continue? So I'm thinking the most likely cause of that error is a corruption of the gold film itself that I'm using as a sensor. Could have gotten a little dirty or gotten scratched. But I also looked at the resonance equation to determine what some other sources could be. And it turned out it could have been theta. And accounting for that specific shift, I would have been measuring theta to be about 2.4 degrees higher than it actually was. Or it could be caused by the spectrometer providing a higher wavelength than it actually was, but the spectrometer had been calibrated by Dr. Chandra beforehand, so I'd like to eliminate that possibility. So for error reduction, I can turn off the lights in the room when I'm doing this, because then I can see the light reflecting and make sure that everything's set up well. And then I can also adjust the angle for max absorption because of that. And that will also avoid stray light interference. I can also restart the software often because it tends to get noisy over time. And search for more accurate image analysis software, hopefully automated, and also clean all of the devices frequently. And work quickly when I'm working with liquid because it may evaporate since plasma is very hot. So my next data set is the more important data set, which I'll be using to actually determine if this setup is a good measurement setup. So the new gold film that I introduced should hopefully have no corruption that would cause an error. And then I'm taking the data at a consistent angle. Excuse me, talking so fast. So that they can be compared on one plot together, visualized together, and I can actually do some graphical fitting this way. So this was me beginning that process, but every time I was changing the media, I was taking the metal film off, cleaning it with a Chemtech wipe, and then putting it back on. And I realized halfway through that was a bad idea because I was probably scratching the gold film. And I was probably also messing up the angle of incidence in between cleaning. And I could have also been getting stuff from the cloth onto the film. So instead, I decided to use an air duster. So instead of taking it off and doing that, I squirted some water onto the film as it was in place, dried the area with a Chemtech wipe, but didn't touch the film with the wipe. And then I dried the wipe with an air duster. So this is my raw unfit data as seen by the spectrometer, and then I just put it all in one plot, wavelength versus percent reflectance. And this time I also created a mixture with a 1-to-1 concentration of pure water and 91% isopropyl alcohol. Then I was able to fit the data, and it looks very nice. And I use these resonance wavelength values to calculate the N values, measured N values for each adjacent media. I got the graphical uncertainties and the analytical uncertainties as calculated from the propagation that I showed earlier. And then I was able to do X and Y, so wavelength, and I also knew the angle, obviously. X and Y. So the change in the reflective index and Y was the change in lambda. So this plot here tells us about the sensitivity of the system. So here's my error analysis of this polynomial fit. Unknown is just the alcohol that we had in the lab. We don't know the actual refractive index of it, but I assumed it would be 1.36, just like other alcohol. Oops. So once again, I had an average shift of about 0.04 here, 0.05 between the measured N and what was expected. I also had around a 3% error, which is normal, but not for measurement. But after accounting for that shift, I got very low percent errors, which is fantastic. And as soon as we can figure out what's going on with the shift, this will be a great system for measuring. It's also good to note that these percent errors are pretty consistent, which is different from the first data collection. They had a wider range. So as I was saying, I can plot the change in lambda over the change in N, and I can get sensitivity as this slope, which was determined to be 2,500 plus or minus 200 nanometers for every increment of 0.04 refractive index. So that is a high sensitivity but it's only for increments of 0.04. So if water's N value is 1.33 and alcohol's is 1.36, an increment of 0.04 is just not precise enough. But the Python code that I created isn't powerful enough to interpolate smaller increments. It can't handle it and it freezes, so that will need to be worked on. So it is a very sensitive system, but how it is so far, it's not very precise yet. So final conclusions. The average error of 3.374% or shifted 0.116% of that polynomial fit proved the SPR setup to be a highly accurate measurement method. The linear least squares fit told us that we have a sensitivity of 2500 plus or minus 200 nanometers per 0.04 inch shift. So although it is highly sensitive, it is not yet highly precise, and I think that is due to the Python code. And we've still got that systematic shift of about 0.045 and it occurs in every data set analyzed. The source is still unknown and requires further research, but it's probably due to either the Python code or corruption in the film. And a summary of my whole research. So I first tested the setup by using just collecting some measurements and making sure I'm getting reasonable estimates. Then I got a new gold film, cleaned it with an air duster between angles, took same angle measurements. And then I analyzed that data and got a sensitivity of 2500 plus or minus 200 nanometers per 0.04 shift in refractive index. And I still got that systematic shift in every data analysis that I did. So I decided that the Python code has low precision and that needs to be worked on. That could perhaps also fix this in shift, but further research does need to be done. But since I do have a highly sensitive system, this setup can continue to be used in Dr. Chandra's lab from now on, and research can be done more so that we can figure out this cause of shift and how to make the system more accurate and precise. So thank you so much for your time today and for sticking through this and your interest. Special thanks to Dr. Chandra for all his help as my research guide, Dr. Hester for teaching the senior capstone course and being a great professor, Office of Student Research for their funding, and Cameron Welch for some of his help.